Good morning.
Hey, good morning. That sounds like Kristen.
It is Kristen.
I haven't quite got things lined up here. Maybe I need to push a button. I don't know.
What's wrong? I mean, I can see you and everything.
Oh, you can see me, really?
Y yes, sir, I can.
Well, I can't see anything. It just says launching, click here or something like that.
Huh, that's
Wait a minute.
strange. No,
Open Zoom. Hey, here we go. Here we go. There we are. Yeah. Pin video. By Jove. Now let's see. I think I need to move this closer.
yeah,
Yeah, to make it, I need to make it bigger.
that's better.
Now, wait a minute, I shouldn't have touched that. Oh no, I touched something and everything is all. Okay, what did I do wrong? What things were going so good and then I touched it.
It
Hmm.
happens to me a lot.
Well, what it's got now is my email. I don't want my stinking email on here.
Well, I can still see you and your board. I don't know.
Really?
Yeah.
Oh gosh. Well, I want to get this email stuff out of here. Maybe if I touch Pat Green, oh, that's my boss. I need to read my email someday.
Yeah, me too. That's something I should probably actually do one day. I don't know.
Oh,
Maybe.
gosh. Okay, well, here, let me, I want to get out of that, whatever that is. I'm going to click on this. I might lose you for a minute. I don't know. Maybe not.
Okay.
Uh, oh, wait a minute. Wait a minute. You're back. Look at here.
Oh, I never left, actually.
Yeah, you never left.
No.
Okay. There, that's pretty good.
Yeah,
Yeah,
like I said, I could see you the whole time. That's
great.
strange.
Well, there's the board, but is it clear? Can you see the board okay?
Yes, sir, I can.
Good. And Sam just joined us too. Good deal, Sam. Let's see who else we got here. We have Sam and Kristen. That's it so far. Well, okay.
Yep, we're the most dedicated, obviously, you know.
Yeah,
I think that should be worth some extra credit right there.
it should be. Uh,
It should.
I'm going to put your homework score on Blackboard. I've got them all worked up. I just haven't put them on Blackboard, but I will. You'll see.
Okay.
It'll be totally efficient operation.
Yeah, I actually looked at that right before I logged in just to see if like you had, uploaded that stuff yet.
Right. I will. And I'm going to work on all my classes, all four of them. I'm gonna try turning this other little lamp off and see if that makes any difference. Does does that reduce the glare any? Not really.
No, it's about the
That
same,
doesn't
but
help.
it's not bad.
I'm gonna turn it back on, I think. Okay. I'm gonna go get my cell phone just in case something bad happens like it did the other day. I'll be
Okay,
back.
I'll be here.
I'll be back. it's only 66%. I don't think it's charging very good. That's not good. Okay, I've got my cell phone in case I need to call my daughter in a panic.
Yeah, hopefully there won't be any panicking or anything, and we'll just have a
Yeah,
nice smooth class,
yeah, right.
especially since our last dynamics class.
Yeah, you know what? This is our last dynamics class.
It is our last dynamics class.
Wow. So we need to do a good job.
Oh, for sure.
Well, I plugged in this cell phone, but it's supposed to have a little lightning stroke sign there. But oh well. Hey, wait a minute. It just went ding ding. So maybe it is working. I'm hoping. Okay, well, we'll worry about that later. Okay, now what I want to do today is I want to work to death a problem. I want to do it with using all our methods. I want to use kinematics. I want to use kinematics, Newton's second law, work energy, and impulse momentum. There are 4 methods. This one here is the last one. And this is called the impulse momentum method. Now, I know you know kinematics, and Newton's second law is the most important thing of all. But I thought we could work a problem and just bore you out of your gourds. Just go over the bonehead basics. There's only 3 of us. There's Sam, Kristen, and me. But we have 4 minutes to go. Now the one I'm going to do is I forget what I told you guys to do. What did I tell you guys to do?
You told us to do F19-5
Okay,
and R19-3.
good, because that's exactly what I want to do. I want to do F 19-5. And so I'm glad you worked on it, because I'm going to work on it. I'm going to do all 4 methods. That's the plan. All right, well, let me draw this F 19-5 thing here. Okay. Yeah. Let's try again. There's an art to this. That's not too bad. And this is at 0.2 and 0.3. So it's really kind of like this. And there's the rope or whatever tied around the spool, the inner axle thingy there. Okay. Now you're supposed to draw 2 diagrams. Now if you draw the other diagram, not very good. But you get the picture. Okay. Now what you're supposed to do is you're supposed to put red stuff on there. Let me get my red stuff. And we have 150 newtons right here. Put that in red. Now this right here is the weight. Now if it's 50 kilograms, does that make 490 newtons? Let me try that. 50 times 9.81. Yeah, it's 490.5 newtons. Of course, you'll have a 490.5 going here. And there will be some friction. Yeah, there's some friction right here. There's the friction. Of course, that would be the 490.5. Okay, I put them all in red. And this one here, gosh, that's pathetic looking. I'm ashamed of that egg-shaped thing there. That's no good. I got to make that better than that. That's a little better. Okay. Yeah, a little better. Now this one's going to have an I alpha. And it's going to have an MA. There you have it. Okay, we've drawn our two diagrams. We put some red stuff on there. Now there's a floor here, or a surface. There's a surface there. And this is point A here. And this is point G. And this distance is 0.2 meters. And this distance is 0.3 meters. Okay, well now let's get the moment of inertia about G and A. Here we go. Now about G we have 50 kilograms. Hey, we got a whole bunch of wonderful students that just logged in. Alex, Cameron, Caitlin, Dalton, Daniel, Gavin, Kristen, and Sam. Yeah, Julian. We lost Kristen, though. That's too bad. Kristen, where are you?
I'm still here. I didn't go
Yeah.
anywhere.
Yeah, she's still with us. Well, welcome back. We're doing dynamics today. And it's Wednesday, April the 29th. And we're just going to work this problem F19.5, using all our methods. We know that we have kinematics. Now, if it's rolling, you can write write V equals R omega if it's rolling. You can write A is equal to R alpha if it's rolling. Those are kinematic equations. And we can do Newton's second law equations. We'll get to those. Work energy. And this, you're really not familiar with that, but we'll talk about it. It's the impulse momentum equation. It's actually the angular impulse momentum equation. We've studied the linear impulse momentum equation. Okay, well, now I'm trying to get the moment of inertia about G. Here's G right here. And they said the radius of gyrations 150 millimeters. So you go 0.150 meters and you square it. And we'll get our radius. No, we'll get our moment of inertia. Here we go. 50 times 0.15 squared. Da-da, I'm getting 1.125 kilogram meter squared. I wonder if that's right. Somebody say, uh-huh. Nobody said anything.
Yes, sir. That's what I got.
Okay. Wait a minute. I put the wrong, I think I put the wrong thing here, guys. It's supposed to be 175. Where did I get the 150? That's not right. I need you guys to help me here. This is wrong. We're doing problem F19.5, and they said this is supposed to be 0.175. I need you to wake up. Okay, now let me do this again and get it right. Here we go. 50 times 0.175 squared. I'm getting 1.53125. Guys, don't believe everything I put on this board. Check me, double check here. I think it's okay now. I think it's okay now. All right. Well, I think that's all the information. Now we're just going to work it to death. We need I of A. Well, see, A is down here. It's the ICZV, instantaneous center of zero velocity. And it's going to be IG plus the 50 kilograms times the distance between A and G. Well, that distance between A and G is 0.3 meters. So you go 0.3 squared and you get, let me get my answer here. You'll have to add that to this. Well, I got an answer. I'm getting 6.03125 kilogram meters squared. Okay, great. Well, let's do it the way the book wanted us to do it, and then we'll do the other methods. The book wanted us to use this method here. Now, to refresh your memory, that's called the impulse momentum method. And we learned the linear, by the way, that's wrong. That's got to be an M. Somebody could have gotten a thank you point. Now it's correct. Now, here's what we learned when we were younger and better looking. We did learn one that had an F in there. But see, that was the change in linear momentum. See, this right here is called the sum of the linear impulses. This is the impulse. This is the sum of all the linear impulses, and this is the change in your linear momentum. Man, there's a bad glare right there. You know where that glare is coming from? It's coming from my computer. That's where it's coming from. I wonder if I could, let me see if I could, you know what? I think that helps a little bit. Yeah. That helps somewhat. But we're not going to use this. We're going to use this one here. This is called the sum of the angular impulses. See, this one here is the sum of the linear impulses. This is the sum of the angular impulses. This is the change in your angular momentum. This is the change in your linear momentum. But we're not going to use it. Well, we could, but we're going to use that one. All right, so here goes. We're going to do that one. And we'll get our answer. Then we'll use these other methods. So here we go. We're going to take the sum of all the angular impulses. The name of this is impulse. And we're going to take the change in the angular momentum. And now, what this is the final minus the initial. But it starts at rest if you read the problem. So what this will be is the final minus 0, because it doesn't have any momentum if it's at rest. Now let's write this. We're going to write this about point A. And we're going to take the moments about point A. Well, look, that force and that force and that force all go through A. They don't give you any moment about A. The only one that gives you a moment about A is the 150. 150 newtons. And we have to multiply that by the distance from A to the force, which is, well, it'd be 0.5 meters. I mean, if it's 0.3 meters to here and another 0.2 meters to there, that makes 0.5 meters. And by Jove, we're done. We got that. Now that's clockwise. There's our equal sign. IA, we just did it. It's 6.0 blah, 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 blah. Kilogram meter squared. Times what? Well, times omega. I think that's what they want. They want to know what omega is. Read the problem. Let me see. Let's see if that's what they said. Spool rolls without slipping. Determine its angular velocity 3 seconds after it starts from rest. Okay, here's where I goofed up. I made a mistake, and it's right in here. Can anybody tell me the mistake I made right in here? While I have a sip of water, I made a mistake right here. Something's missing right in here. What is it that I'm missing? You could get a thank you point for this. Well, nobody's going to answer, so I'll pick on somebody. Gavin Jackson. Gavin, can you hear me? Unmute.
Yes.
Gavin, I forgot to do something right in here. What is it that I forgot?
Integrate.
No, but that's an intelligent idea.
Or
No.
multiply by time. I'm not sure.
Say that again, Gavin.
I said or multiply by time.
Yes, that's what I forgot. If you read the problem, they said that this thing is going to go for 3 seconds, and I didn't put the 3 seconds in there. So we're going to squeeze it in here. Let me squeeze it in. There, Gavin figured it out. See that time right there? I didn't put the time in there. Now this moment is a constant, so I don't have to integrate anything. You can just pull it out. It's going to be 150 times 0.5. You know what that is? I can do that in my head. That's 75 Newton meters. but you have to multiply it by the time. See, impulse is your moment times time. Okay, now we got it. Put this into your calculators. Can you all see that? I bet you can. And solve for omega. Here we go. 150 times 0.5 times 3 divided by 6.03125. Okay, if we did that right, of course, this is clockwise too. I'm coming up with an omega equals 37 point, I don't know, we can round it off to 3 radians per second. Okay, now let's see what the book got. We'll see if that's what the answer book says. Let me dig out the answer book here. And then we'll do it a different way. That'll be fun. This was problem F 19.5. And they said the omega is 37. Well, boy, Jove, the book got 37.3 radians per second, just like we did. So far, so good. Now we're going to do it a bunch of different ways. We just did it this way. Here, I'll put a little check mark on there. Check. We just did this method here. Now, this method has a name. It's chapter 19, in fact. And it's our last chapter. We really haven't studied it much. I think today we're doing a little bit in 19. But the name of that is the impulse momentum method. And we did it right. But now let's do a different method. Let's do the Newton's second law method. Okay. Well, I need a little room here, so we're gonna scrap some of this stuff here. Let me write this down over here where I can find it. IA is 6.03125. And that way I can get rid of all this stuff here. Before I erase everything, did anybody have a comment or question before we do the Newton's second law method on this problem? I guess you're happy. If you're happy, I'm happy. Nobody said anything. Okay, well, I need this space in order to write these wonderful equations. So there we go. Newton's second law. Okay. We're going to write it like this. The sum of the moments about point A is equal to IA alpha because it's rolling and it has an ICZV at A. Otherwise, there's another term that you have to add on here if it's not rolling, if it's slipping or sliding. But we got that. We're okay. So let's write it. Here we go. Moments about A. Well, that force goes through A, that normal force. That doesn't give you a moment. The friction, we haven't solved for the friction. We'll do that in a minute. Won't that be fun? We'll get the friction. But it goes through A, so it doesn't give you a moment. The weight, the 490.5 goes through A. It doesn't give you a moment. But the 150 does. So we have 150 times, well, it'd be 0.5, wouldn't it? 0.5 meters. We don't multiply by time this time. Remember last time I had to multiply by time, the 3 seconds? But we don't have any time, it's just the moment. So there's your newtons, there's your meters. I wrote this down so I could find it. 603,125 kilogram meter squared alpha. Hey, we can get alpha. Okay, well, let's do it. Here goes. I'm going to find alpha now. 150 times 0.5, 6.03125. I got alpha. My alpha is 12.4, I don't know, 4 something, 35 radians per second squared. So we got our alpha, but that's not what they wanted. They wanted omega. But there's a relationship. It's a kinematic relationship. It goes like this. Omega equals your beginning initial omega plus alpha times the time. That's a kinematic equation. It might be helpful if you memorize the linear equation. It goes like this. The linear kinematic equation, I'm sure you've seen this equation before. V equals V0 plus AT. You should have that memorized. That's the linear kinematic equation. This is just the angular equation. It's the same kind of equation, but it's for angular velocity. This is linear velocity. This is angular velocity. But we don't have any initial. So our omega that we want is just alpha times t. Okay, get rid of that initial omega. We don't have any. So we can get omega is just equal to alpha times t. Well, alpha, we think, is 12 point blah, blah, blah. And t is 3 seconds. You read that in the problem. Okay, multiply that. And if we're very lucky, we'll get the same answer we got last time. I erased it, doggone it, so I don't know what it is. Do that. And then somebody tell me what it is.
$37.3.
Well, Shazam. You know what? That's what we got the last time. 37.3, Kristen?
Yes, sir.
I think that's what we got the last time, wasn't it?
Yes, sir, it is.
Yay! Hey, we just figured this problem out using Newton's second law. Here, let's put a little check mark there. Check. Now we've done it with the impulse momentum method. And now we've done it with the Newton's second law method. But we got the same answer. It's the same answer the book got, but see, we don't need no stinking answer book, do we? Not if you can do this problem one way after another and get the same answer. You know you did it right. It's called checking your work. It's a fairly new concept with some of my students, but I think it's an important one. While we're at it, why don't we go ahead and find out what this frictional force is? That would be fun. I need some room to do that. Let me write this up here in the corner someplace. And we can make some room. IG is 1.5 blah blah blah. Okay. So I'm going to make some room here. And we're going to find that friction force. And here's how we're going to do it. We're going to use this formula here. Now, does anybody know the name of that equation? The name of that equation, I wonder what that could be. What do you think? We're going to go to my friend Sam. Sam, what's the name of that equation? You can do this, Sam. I have faith in you. What's the name of that equation? Unmute. Sam.
My mind went blank when you said that.
Hey, my mind goes blank all the time. Now, Sam, I need to know the name of this equation. Go for it. Sam, I'll give you a hint. It's the most important equation in our class. It's numero uno. I'll give you another hint. It starts with the word, no, the first letter of it is N, starts with N.
Is it Newton's?
Yeah, go.
Newton's.
Newton's. Keep going, Sam. You can do this.
I want to say
Yeah, say that again. Newton's
second law.
Newton's second what? Newton's second.
Law?
Yeah, yay, Sam, got it. Good going, Sam. You know what it is? It's Newton's second law. Maybe I forgot to tell you guys, but if you ever get stuck in this class and you don't know what to do, just go to Newton's second law. That'll take care of everything. Okay, we're going to use it now. Here goes. Now that Sam's helped us out, we're going to get all the forces. I'm going to do these in the x direction. So get rid of the vectors and just look at the scalar amounts. Now in the x direction, we have 150. Sam knew that. It's just that when you're asked something, your mind goes blank. It happens to all of us. Okay, but wait a minute. We also have another force going to the right. See, there's two forces going in the x direction. X direction is going over here to the right. And there's our equal sign. And then we have our mass, 50 kilograms. Now the A, remember the A is equal to R alpha. If you want the acceleration of the center of mass, then you take the R, which is 0.4 meters, times alpha. We got alpha. There it is. It's 12 point blah, blah. Guys, we have an equation in it now. This is Newton's second law equation. It's his linear second law equation. Newton also has rotational second law equations, doesn't he? But this is his linear second law equation. Get your calculators and solve for friction. I'm going to do it. I want you to do it. We'll see if we get the right answer. Here goes. On your mark, get set, go. Hope you can read my writing. Must have done something wrong.
I'm sorry, where's the 0.4 coming from?
Isn't it? There is no point. There is no 0.4. That's a mistake. I'm going to give a honking thank you point to Kristen. What we need is 0.3, Kristen. See it? I don't know where the 0.4
Yes.
came from.
Yeah, I see that, but I was just like, I was looking at my paper. I'm just like, I don't have that anywhere. Okay, thank you.
Thank you. The whole class thanks you. Kristen helped all of us because there is no stinking 0.4 any place that I know of. All right, now do that. We'll get the friction. Here goes. All right, here goes. See, it really helps if you stay awake here. Now I got my friction. I got 36.525. Wonder if anybody. I'm going to wait till I hear a couple of uh-huhs. I need a couple of uh-huhs. Let me see who's out there. Participants. We got some wonderful students here. There's Julian there, Mohammed, Daniel, Cameron. Surely one of you guys can give me an uh-huh.
That's what I got.
Yay! Somebody got it. So
That's
we
what I
think-
got.
Yay! We think we know what the friction is now. Excellent. We know the angular velocity. We know the angular acceleration. We know the friction. We know the time, 3 seconds. We know a lot of stuff. Well, I'm tired of Newton's second law. Let's, well, no, I'm not tired of it. There are several versions of Newton's second law. Let's show you the others, and then we'll move on to the last method. Because see, we've done impulse momentum, Newton's second law, and we've done kinematics. We haven't done work energy, but we will. That'll be good. But there's a couple of other Newton's second law methods. Let's do those. Okay. Let me write this friction up here in the corner where I can find it. Because I need the space. Now I'm going to erase this stuff to give me some space. Now wait a minute. Let me write this omega. It's 37.3. I need the alpha too. That's the alpha right there. Okay. We'll keep all of those wonderful things up here in the corner where we can grab them. I'm going to erase all this if you're happy. Speak up if I'm going to erase it. Okay, 5, 4, 3, 2, 1. All right, nobody spoke up. I'm going to erase all this, and then I'm not quite ready to leave the Newton's second law method. See, there's another version of the Newton's second law method that we haven't used on this problem that goes like this. That's just as much Newton's second law as the one that Sam told us about. And we have not used that particular version. It's Newton's second law for rotation. See, this is called, it's the moment of a force, the total moment. That's the sum of all the moments about point G acting on the body. And this is the moment of inertia about point G, the center, or the center of mass. That's your angular acceleration. Well, let's try it. Let's see if it works. We know it works, but let's do it. Okay, now the moment's about G. Well, this force goes through G, but now wait a minute, you're going to get a 150 newtons times, and this time I'm going to try not to screw up. Remember, I put a 0.4 in there. I think we need a 0.2 is the distance from G up to where this force is. Ah, but you're not done yet. You've got the friction. Now see, this is clockwise. You're going to have to go minus the friction, which is 36, blah, blah, times the distance from G to the friction, which is 0.3. Uh-oh, I'm running out of room here. Equals IG. That's the, we'll just slant down. We'll be okay. 1.53125 times alpha. Oh, look here. Here's an equation with only one unknown, and it's alpha, the angular acceleration. Get your calculators and do that for me. And if we're very, very lucky, we should get this same alpha that we got before. Go for it. Well, I just did that. I solved that and I got an alpha. I got 12.435. I got the same answer for alpha that we got before. That's good. That just means that that particular way of writing Newton's second law works just fine. There's another way of writing Newton's second law. Let's do that, shall we? Let me scoot this 150 out of my way here. We have not written Newton's second law like this. There are several ways of writing Newton's second law. This way here, we just used, but we have not used this one here. Let's do it. We're kind of checking our work here. Okay, now we're going to take the sum of the moments about A. Well, there's A. The friction doesn't give you a moment about A because it goes through A. Did you know that a force that goes through a point does not give you a moment about that point? This normal force, this 490.5 of the floor pushing up goes through A. It does not give you a moment about point A. The weight, the 490.5 goes through A. It does not give you a moment. Ah, but the 150 does. Well, we just did that. We already did that. No, we didn't. We did the moments about G. The moment about A is different. It's 150 newtons times, in this case, 0.5 meters, isn't it? That's different. Because from A up to this force is 0.5 meters. Okay. Now here's IG. Well, we know what that is. That's 1.53, blah, 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 times alpha. Why don't we just write it like that? Plus R. Now this R is going up to the G. See that MAG? There it is, right there. There's your MAG. We're taking the moment of that kinetic force. This thing has a name. It's called a kinetic force. This is called a kinetic moment. And we're going to take the 0.3, so it goes 0.3 times 50 kilogram. And see, AG can be written, I erased the equation, but it can be written as 0.3 times alpha. See, AG can be written as R alpha. I wrote that earlier for you. Okay, now here we have an equation with only one unknown. What we're doing is we're boring you by checking our work and going over our equations that we know and love to see if they give us the same answers every time. Okay, plug all of that into your calculator and tell me what you get for alpha. I'm going to do it. Here goes. Well, I did that and I got an alpha. I got an answer for alpha when I plugged in this equation, and I got 12.435. How about you? I see Alex there. Alex, tell me, did you get 12.435, Alex, when you plugged that in?
Yes, I did.
Yay, good going. Well, now I'll tell you what we've done. We've done this problem. This is fundamental problem 19.5. We've done it with the impulse momentum method. We've done it with Newton's second law several ways. We've used the various versions of Newton's second law, and each one of them seemed to work pretty good. But I tell you what we haven't done. We haven't done this method here. Now, this is called the work energy method or the work energy theorem. And I thought I would do that. I need a little room to work here, though. We got all our answers. We got alpha, we got friction, IA, IG, omega. I could erase all this stuff and we could write the work energy method. Here goes. Unless there's an objection, I'm going to erase all this because I need the space. Well, I didn't hear any objections, so we'll say goodbye to all of that for right now. And we're going to use the work energy method. Let me tell you a dirty little secret before we use the work energy method. When you do problems in dynamics, if they give you the time in the problem, you want to use the impulse momentum method. Uh-oh, I ran out of room here. If they give you the distance in a problem, you want to use the work energy method. If they don't give you the time or the distance, they just give you a bunch of forces and maybe weights, coefficients for friction maybe, but they don't give you the time or the distance. You want to use the Newton's second law method. You'll find that problems, if they give you the time, are pretty easy with the impulse momentum method. We did that. We did this impulse momentum method, and bam, bam, bam. It was pretty easy, I thought. But now we're going to use the work energy method. But see, we need the distance. We need the distance to do this method. If they give you the distance, that's a beautiful method. We don't have the distance, so we're going to have to find it to use the method. Okay, so there's just a little rule of thumb in problems. But you can use any of the methods. All of the methods work. It's just that some are easier to use. Some are easier to use. But right now, we're going to do fundamental problem 19.5, and we're going to use the work energy method. This is called the work energy. Uh-oh, I'm running out of room here. It's the work energy thing. All right. Well, to do it, we need the distance. There's only one force that's doing any work. This weight doesn't do any work because it's not going up or down. It's a spool. It weighs 50 kilograms. That's pretty heavy. Oh, man, I think that's over 100 pounds. But it's not going up or down. That's not doing any work. And this normal force, the force of the floor or the surface, it doesn't push up or down, so it's not doing any work. And now the friction, because it's rolling and not slipping and sliding, it doesn't do any work either. For it to do any work, you have to have relative motion. There isn't any. It doesn't move. The spool doesn't move relative to the surface because it rolls. The only thing that does any work is the 150 newtons. But how far does it travel? Well, I can tell you how far the G travels because we know the formula. Distance is equal to V sub O T plus 1/2 AT squared. You guys remember this from long ago? Can you read that? Maybe. But see, there is no initial velocity. It starts at rest. So you don't have any initial velocity. The distance that G, the center of gravity travels, will be 1/2 AT squared. Let's scoot that over there like that. We need that. Okay. Well, we can get this. The acceleration of the center of gravity is R alpha. Okay. Well, what's R? Well, that's the 0.3. So that's 0.3 times the 12 point blah, blah. We can get the acceleration. Okay, well, let me do that. 0.3 times 12.435. Did you get the acceleration of the center of gravity to be 3 point blah, blah, blah meters per second squared? See, that's meters. And so we can get the distance that the center of gravity travels in 3 seconds. They said 3 seconds. So you go 1/2 the acceleration times 3 seconds squared. Well, let me do that and we'll get the distance. Here goes. 1/2 times 3.7305 times 3 squared Did you get the distance that the center of gravity travels? 16.7 blah 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 meters. Now what's a little bit tricky is that's not the distance that the force travels. It travels a longer distance. See, it's going faster. See, everything's rotating about this point. Everything. This will have a little velocity going to the right. But see, the velocity here is bigger, but the velocity here is bigger. It goes it's unwinding. See that? It's kind of like a yo-yo. That string there is, as you're pulling it, it's unwinding and it goes a longer distance than the G goes. And I can tell you the ratio going from here to here, it's 0.5. From here to here, it's 0.3. So if you want the distance that the force goes, and that's what we want because work is force times distance, it's going to be 5/3 times a 16.787. There's other ways to arrive at that, but see, does that make sense to you? That this string here goes a longer distance than the G goes because it's unwinding. Okay, well, let me get that distance. Here we go. 16 times 5 divided by 3. That force acts over 27 point blah blah meters. Now we can use the work energy method. Here goes. I just need this room right here. The total work done on this body is the 150 newtons. It's the only force doing any work, times 27.979 meters. And that's got to equal the change in kinetic energy of the body. Well, the change in kinetic energy of the body is 1/2 IA omega squared. Well, we got IA, it's sitting right here. Look, we know what that is. We got that a long time ago. See it? We can solve for omega. Put that in your calculators and solve for omega. On your mark, get set, go. All right, I'm plugging all this stuff in now. Then I have to take the square root. Okay, I got an answer. I'm getting 37.3 radians per second for your angular velocity. Guess what? That's what we got all the other, when we did all the other methods. Is there any comment or question about that? Well, nobody seems to have any comments or questions. Let me give you one last thing to do here. And I just need some room to do it in. Here's some right here. I'm going to give you, we got lots of time. We got plenty of time. There's no hurry. I'm going to give you time to do this. I want you to find two things for me. I'll just shut up and let you work. I want you to find the kinetic energy of translation after 3 seconds and the kinetic energy of rotation after 3 seconds. Okay. I'm going to let you see. I want to see if you can do that without any hints or anything. I'm going to shut up now. In fact, I think I'll go. I don't drink coffee, but I'll go have a pretend cup of coffee. Maybe I'll make some Pero. Have you ever had Pero? It's kind of a barley substitute for coffee. Only I joke and say that coffee is a substitute for Pero. Okay, I'll give you at least 5 minutes. I want you to find the kinetic energy of translation and the kinetic energy of rotation. Here, I'll give you some humongous hints. This is 1/2 mv squared. You knew that. And this is 1/2 ig omega squared. Okay, find those for me. You have 5 minutes. Oh, I needed to stretch anyway. All right. On your mark. Get set, go. Oh, that's, oh, I think that gave me a heart attack. I think I'm gonna die now. Wait, I wanted to finish my class, but I'm gonna die. That's too bad. Students, I'm sorry, but my grandson scared me so bad that I'm dying. All right, and he's laughing about it. That's not very good. You give me a heart attack and then laugh about it. Okay, well, welcome back, everyone.
You didn't even see me.
No, I didn't see it. Okay, we're going to get our answers now. And we're going to find the, I need some room here. Let me get rid of some of this. That was a lot of fun. Okay, kinetic energy of translation, that's equal to 1. Here, we'll put a little TR A in there. That's equal to 1/2 the mass, 50 kilograms, times the velocity. Well, now the velocity is going to be 0.3 times omega, which is 37.3. It's 0.3 meters times 37.3 radians per second. But see, you have to square it. Okay, let me do that. Here goes. We're going to find the kinetic energy of translation. 0.3, 37.3. Okay, I got an answer. Holy cow, I'm getting a humongous answer. I wonder if that's right. Did anybody get 3130 joules? Or did I do that wrong? Somebody, if they got 3130 joules, speak up. Nobody's speaking up. Everybody probably, they're probably taking a break, taking a walk outside or something. How about Daniel? Daniel, unmute. And did you get 3130 joules? Daniel?
Yeah, that's what I got.
Yay, good going. Okay, now let's get the kinetic energy of rotation. Now what that is 1/2 I of G. It's the 1.53 blah, blah, blah times omega squared. Now there's omega, 37.3 squared. Okay, we're going to get the kinetic energy of rotation now. 1/2 plus 1.53125, 37.3 squared equals, it's pretty big too. I'm getting 2,130.9 joules. Let me pick on Don again. Don, you helped me out before. Unmute. No, not Don. No, it wasn't Don. He's not in my class. Don's not in my class. It was Daniel. Daniel, unmute. Did you get 2130.9, Daniel?
I got about half that.
Gee, I wonder what I did wrong. I went 1/2 Ig times omega squared. Let me do it again.
Yeah,
1/2.
I keep getting 1065.
Okay, I must have pushed the wrong button. Let me try it again. Just a minute. Times 1.5. Okay, 1/2 times 1.53125, 37.3 squared. 1065. You guys, both of you guys are right. There's a little room over here. 2 thank you points. I don't know. Maybe I forgot to multiply by half, you suppose? I bet that's what it was. I don't want to use my thumb to erase because this computer, believe it or not, to get it to turn on, I have to put my thumb on it. Have you ever heard of such a thing? I have to put my thumb on this little place, and if it reads my thumbprint. What do you think of that, guys? Does anybody have a computer like that? I just bought
Not me.
I just bought this, I think it was yesterday, with my money I got from President Trump. Did any of you get any of that money? He sent out a bunch of money. I don't know why he sent me any money. I don't need any money. I still have a job. I still get paid, even though I'm doing this at home. I'd rather be with you guys at school, though.
It's to stimulate the economy.
Okay. Well, I got 1065. 0.2. Uh-oh, I ran out of room there, but those are joules. Now, I want to tell you guys something interesting. If you'll add those up, you'll get the total kinetic energy. And it should equal this total work done. See this here? Let me see what that is. You know what this is? This is the total work done. 150 times 27.979. I'm getting a total of 41, I think I'll just round it off to 97 joules. That's the total work done on this body. Now, when you add these two up, if we're very, very lucky, it should be 4197 joules. Let's see if it is. Add up the 3130 and the 1065. And here's what I'm getting. When I added those up, I didn't get 4197. I got 4195 joules. I bet that's pretty dang close. I bet I rounded off someplace along the line. I probably rounded off. I think we're okay though. Here's the rule, guys. When you put in 3-digit numbers, if you have 3-digit accuracy, if you round off to 3 digits and you get an answer, don't expect 4-digit accuracy when you're inputting 3-digit numbers. Make sense? So I think we did okay. We have that. Now let me show you one last thing here. We've had a wonderful time here. I think this is a good preparation for your final. I'm going to post the finals Sunday night and get my daughter to help me post them. They'll be due Wednesday night, and I'll be grading them on Thursday. So I'll have plenty to do, won't I? But let me show you one last thing, if I can just find a little room here. Yeah, we got lots of room. Before I erase all this wonderful stuff, do you have any comments or questions? Well, okay, I'm going to erase some of this because I want to write down something here. Yeah, made a lot of room here. We can write in here. See, the total kinetic energy is equal to the kinetic energy of translation plus the kinetic energy of rotation. And we just figured all three of these. This was 41.95 or whatever. This one was 31.30, and this one was 10.65. Do those add up pretty good? Yeah, that's pretty good. Yeah. But see, you can also get the total kinetic energy another way. I've told you this. It's just that I believe in telling you stuff over and over and over. I don't know about you, but I can't learn things the first time around. It takes it over and over and over before I learn. And then sometimes I don't learn. But it's worth a try. There's another way to get the total, but the thing is, this only works if you have that ICZV thing. And it's equal to 1/2 I about the ICZV omega squared. Well, in this case here, this is your ICZV. Point A is the instantaneous center of zero velocity. And so you can go 1/2 6.03125 times omega, which is 37.3, and square it. Put this into your calculator, and if we're very, very lucky, it'll be 41.95. Let's try it. Here goes. Let's see, 1/2 times 6.03125, 37.3 squared. Well, boy, Jove, I'm getting 41.95 doing it that way. So you can get the total kinetic energy of a body that has a fixed pivot or an ICZV that way. Or you can get it by doing the individual translation and rotational amounts. Any comments or questions on that? Okay, well, let me show you one last thing here. I keep saying that. This is just one last thing. I'll show you one last thing. It goes on forever, right? It's like one of those bad dreams. See, we have a body. Oh, that came out pretty good. That's not too bad. And see, it's rotating about point A, which happens to be the instantaneous center of zero velocity. It's rotating. So if you had a point over here, for example, draw you a line there. There you go. You know what? The velocity of that point is like that. Say this was point B. The velocity of B is like that. Now, if you had a point over here, there's your distance. That's going to be perpendicular to that. It's going to be kind of like that. And you know what? It's a little longer. Call that point C maybe. The velocity of C is going to be bigger than the velocity of B because it's equal to R omega. Now the omegas are the same. Every portion of this body is rotating with the same omega. The omega is the same for every portion of this body. Now, if you have a point over here, draw a line to it, and there you go. And that's going to be perpendicular to that. About the same. Call that point D. The velocity of D, kind of in the same ballpark as the velocity of C. Now let's take a point over here. Draw a line to that. There you go. Now, this thing's rotating clockwise, so that point will have a velocity pretty small because the R is small. Do you understand this R here is bigger than this R here. And this R here is smaller than this R here. And so you get a smaller velocity. Call this point E maybe. There's the velocity of E. Now the velocity of A is 0 because A is the instantaneous center of 0. There is no R to A. If this is A, you don't have any distance from A to A, it's 0. So it doesn't have any velocity. Now it would if it's slipping or sliding, but it's not. Okay, well, it's sad that our time together is coming to an end. But if you understood all that problem there, I'm not a total failure. If you can work Newton's second law equations and go on to OSU or wherever you're going, I won't be too ashamed of you. I just won't. In fact, I think I'll be proud of you. I'm hoping. Our time is coming to an end, and I'm going to give you your final. You study for your final, and I'm going to get all of your homework and quiz grades posted on Blackboard. I'm working on it. Here's your chance for a last comment or question, and then I'm going to sign off. The floor is open for your questions. Well, nobody said anything. I'm going to scoot this over to where we're going to end the session. When I push this button, I'm going to go bye-bye.
In a couple hours.
Yeah, I'll see you in a couple hours. How about some of the rest
See
of
you
you?
next semester.
Hey, I hope so. I hope I see you.
I'm taking your thermo class, so.
Well, now, did you know I'm teaching that online this summer?
Really, I did not.
Yeah, you're welcome to take it. But if you take it in the fall, the higher ups tell me that I'm supposed to teach a blended class. My classes are blended. What that means that they tell me is part online and part face-to-face. I don't know how it's going to work.
Oh, to reduce like how many people are in the class at one time?
I bet that's it.
That would be the only thing that I could guess.
Maybe that's it. I don't know. I'm not one of the higher ups. I'm just a schmo. Like in the military, it's like being a private, okay? I do what the higher ups tell me to do. Okay, well, I'm looking forward to seeing anybody that wants to take my class. Hopefully I'll still be around. Anybody else, comment or question? Okay, here's your last chance. 5, 4, 3, 2, 1, blast off.